It's a double integral. I'm going to go ahead right now and write r dr d theta. I'm going to write that right now because I know when I go to polar, I'm always going to have r. Then dr d theta, I have choice there in the order, but I'm just going to stick with that. That means my theta is going to be the outside limits. 0, 2 pi is what we're using. And my radius is the inner integral, so the limits there were 0, 2. And then what we are integrating, 4 minus r squared. Bam. Done. That's not worth integrating any further, right? Distributing r through 4r minus r cubed. Integrate, that should be pretty clean. Can I dot, dot, dot this one? Equals dot, dot, dot. That is significantly easier than doing it the other way, which would have been to somehow break up that circle into type 1 regions from last class Cartesian. It would have been a disaster. All right, questions, comments? Y'all look tired. Some of y'all are falling asleep. Please don't fall asleep. Go do some jumping jacks outside or something. I know y'all are like on Easter sugar overload or something, but I am too. I stayed up last night way too late watching, what was that movie with, what's his face? DiCaprio. He's out in the woods all messed up. Yeah, I don't know if I cared for that. I mean, it was okay. I was expecting a lot more. I don't know. I was expecting a lot more. I mean, it was okay.
I mean, the guy won an Oscar for it.
Yeah, it's all right. I was a little let down though.
Maybe you're thinking he deserves it.
The real guy who went through that deserves it. Wasn't that a true story?
Yeah.
Okay, I'm going to leave this problem on the board, but I'd like for us to do a pretty amazing problem. I think this is a great problem. We'll see. Verify that the area of a circle radius r is pi r squared. We all know that the area of a circle is pi r squared. Those of you who've had me for Cal 2, I verified this in Cal 2, but we did trig sub to do it. We're going to do it with a double integral now. So one thing we have to remember is something that we talked about last class. If you want to find the area of some region, capital R, it's equal to the double integral over the region of what function? 1 dA. That I told you in class last time, is that if you replace the function in here with 1, then the double integral of the constant 1 function over some region R is actually equal to the area of that region. Let's use that right now. Okay, what I want to do is find the area of a circle, right? So the region, that's going to be my region. So let's draw it. An arbitrary circle, radius r. That would make a wonderful polar region, wouldn't it? In fact, in polar, my restrictions would be very nice. Theta's between 0 and 2 pi, and r's, ooh, this is r. R is between, we have trouble here. Do you see the trouble we have? I got to use a different R. So why don't we call this, I don't want to use capital R to confuse it with region. I'm just going to use R tilde, all right? R tilde, this is a constant. See, our R here is our region. We're allowed to move through different radii values. So that R that I'm allowed to move through must be between where and where? 0 and R tilde. Everyone understand R tilde is constant? I could have called this R naught. I could have called it anything I want. I chose R tilde. All right, set up the double integral. What does it become? The area of that circle over that region R should be equal to the double integral. It's polar, so I always have to put what in polar? So I'm doing 1 r dr d theta. What's my restriction on r? So I can put that in there and my restriction on theta. Right here. So theta goes on the outside, 0 to 2 pi, and 0 to r tilde. Now, I could dot this one, but it's worth us finishing, right? Okay, what's the antiderivative of r with respect to r? 1/2 r squared. I'm going to evaluate that from r equals 0 to r equals r tilde d theta. Replace r with r tilde, replace r with 0. What would you get? Just 1/2 r tilde squared d theta. And now integrate this with respect to theta. This is all a constant, isn't it? So the antiderivative of that is 1/2 r tilde squared times theta. Evaluated theta equals 0 to 2 pi. Replace theta with 2 pi, replace theta with 0, and you get 1/2 r tilde squared times 2 pi. So that's just 1/2 r tilde squared times 2 pi, which is just pi r tilde squared, which is basically what we were trying to show, is that the area of a circle is pi times the radius squared. All right, so some of y'all are real tired or something because, I don't know, we just proved the area of a circle is pi r squared, and y'all didn't seem too excited about that. So that's not going to get you excited. Nothing else I do today is. Sorry. We did that with relative ease, didn't we? I mean, that took us less than 5 minutes to do with polar coordinates. If you did that in Cartesian, it would involve, trig substitution, and it's doable. It probably takes about 10, 15 minutes to do the other way. All right. Now, this is a picture of a surface, some function of x and y, which we're converting to r cosine theta, r sine theta, which creates like an upper surface, another surface g that creates a lower surface. We're trying to find the volume between these over some polar rectangle. And so this, again, to just remind you what happens here, if you're trying to find the volume between two surfaces, you subtract the two surfaces, which really just breaks down to subtracting the integrals, double integrals. And we can convert to polar and do exactly the same thing. So here's a good example. Find the volume of the solid below x squared plus y squared plus z squared equals 1, and above the cone z equals root x squared plus y squared. So hopefully you recognize the first equation as the equation of a sphere radius 1. So you have this sphere radius 1, there it is. You've got this cone, z equals root x squared plus y squared, which starts at the origin in three-dimensional space, creates this cone shape. We're trying to find the volume of the solid below the sphere, above the cone. So that thing right there looks like a snow cone. right? Does it look like a little snow cone? What's its volume? So how to do this? Any ideas? Any ideas? Sure? You seem kind of... All right.
Get the whole and then subtract the one above the cone.
Do the what?
Find the volume of the sphere and then subtract the volume of the cone.
That's a good idea. Let's think about what's being proposed. If we take the volume of the entire sphere and subtract the volume of the cone, that's not quite a cone though, but you would want to subtract this to get, I think that's what you're getting. I don't. Take a look back at this picture that I just had up here. If I'm trying to find the volume of this chunk of stuff right here, does it have a top cap? Yes, it's the F function. Does it have a bottom cap? Yes? And what about the walls of this thing? That's dictated by the region on the ground, right? So as long as you can come up with some top cap and some bottom cap to the solid, and then you can define very clearly what the region is that you're integrating over, then you should be able to get the volume. So let me take you back to this picture. Do you have a top cap? It's just slow. That's it. The top cap is created from the sphere, right? The bottom of that solid is created from the cone. So you have a top and a bottom, don't you? The question is, what's the region of integration? So you have to look at almost like the shadow of that object straight down. So if I take this object and I rotate it and I look at it straight from the top, right? Then I imagine taking this edge straight down to the XY plane. That's my region of integration. Do you all see that? And that's a circle, yes. So again, I'm going to try and draw it on here. If you translate this thing, this red curve straight down, you get some circle down here on the ground. Okay? Do you all see that circle? What we're doing is we're saying, take a point here, plug it in, right? And if I go straight up and I go in between the sphere and the cone, I will be in the snow cone, won't I? Yes? And I have to pick points all from in here and take all those up to draw the whole picture. Yes? Okay, so how are you? I think we've talked about what the region is. How are you going to find it, though? Is it the radius? Is it the radius of the sphere? No, it's not, right? It's where the two hit each other. It's where the cone and the sphere hit each other. If you imagine taking that and just going straight down to the ground with it. So to start off, to get my region, I first need to find where these two intersect. How could you do that? How could you find where those two intersect? Do it what? Huh? Set them equal to each other would work, but we would have to solve them both for z, and then set them equal, right? Or you can just say, hey, look, to live on the cone, z must be this, right? So just go rewrite that sphere equation, and square z, right? This right here is z squared, isn't it? And then equals 1. So you get 2x squared plus 2y squared equals 1. And that means x squared plus y squared equals 1/2. And that's a circle of radius. It's the radius of this circle. Root 2 over 2 or 1 over root 2, right? Those are the same things. That's your radius. Questions? Regler?
That's a neat trick.
What'd I do?
Oh, I mean with the plugging Z.
Oh, okay.
Z squared.
Yeah, and you could even go a little bit trickier than this if you wanted to. If I know I'm going to polar, which I do, I know I'm going to go to polar on this, right? Then I could just replace x squared plus y squared with what here? R squared. And square root of r squared would be r. And so I could replace this. That first equation becomes what? R squared plus r equals 1. That's a quadratic equation. R squared plus r minus 1 equals 0. And then you could do, how would you figure out what r is there? How about a quadratic formula? And you would get a quadratic formula, and one of your solutions would be this. But we didn't do that. So, all right. We good? Can we draw the region on the ground? Okay. So we could do, we know it's a circle on the ground. It has a radius of, do y'all like 1 over root 2 or root 2 over 2? Does it matter to you? Doesn't matter. Okay, I'm going to use 1 over root 2. I'm still boycotting rationalizing fractions. I've been boycotting them for a long time. All right, polar region. As a polar region, theta is going between, and r is going between. Theta? 0, 2 pi. R, 0, 1 over root 2. So I'm going to set up my double integral. I want you to pay close attention here. This is the double integral I'm trying to set up. I'm trying to set up the double integral over some region R of f of xy minus g of xy dA. That's what I'm trying to do, right? It's between two surfaces, so I'm trying to find the volume between two surfaces. My upper function, f, is the sphere. And that means I need to solve that for z. So go ahead and do that now. Solve this for z. You get z equals square root 1 minus x squared minus y squared. Now, it should be plus or minus, right? But I'm only doing the plus because I'm looking at the top cap, the top half of the sphere. And then this one's already solved for z, isn't it? So this is my f function. And this right here is my g. So this becomes double integral over r of square root 1 minus x squared minus y squared minus square root of x squared plus y squared dA. That's what it would be in Cartesian. Not only would this suck in Cartesian to integrate, our limits of integration would suck too because they would involve a circular region, so that we would have to break it up into multiple pieces, and we'd have like a top half and a bottom half, and it would just be a mess, a disaster. That's the value of going to polar. So if I go to polar, which I'm about to do, I'm always just going to remember r d theta. Okay. My function of x and y is now going to get converted to a function of r and theta. Y'all know what we're going to replace the thing in here? Right, we're going to factor a negative out of those. And it'll be just 1 minus r squared underneath the root. Minus, and this is just going to be r. Limits of integration, theta on the outside, 0 to 1 over root 2.